This visualization captures the current barrier in AI-assisted development. We see digital code particles repeatedly hitting a glass wall. Your local AI coding assistants are powerful, but they are trapped behind that wall, restricted entirely to your local file system. If you want to use those tools to write machine learning scripts for a remote Google Colab GPU, you are forced into a manual copy-paste loop. You generate the code locally, copy it, switch tabs, and paste into the remote runtime. When that remote execution throws an error, the process reverses. You have to manually scrape the traceback text from the Colab cell and paste it back into your local IDE to prompt the AI for a fix. Every time you switch context to move text back and forth, you lose engineering momentum and shatter your focus. The context window breaks at the manual transport layer. GoLab is a pure Golang implementation of the Model Context Protocol designed specifically to eliminate that manual transport layer. Look at this network diagram. A local node representing an AI IDE projects a solid WebSocket communication line straight into the remote Colab UI proxy. Through that connection, the bridge exposes 27 distinct tools, granting full read, write, and execution privileges. It achieves this hardware integration without requiring you to install any complex Python dependencies on your local machine. To understand how this works, we'll break down the deployment tunnel, compare static versus dynamic tool architectures, and audit the repository's production risks. Implementing this server turns a fragmented ML scripting process into a continuous loop of local editing and remote execution. The very first technical hurdle for any bridge software is establishing a clean execution path that bypasses local environment bloat. Because the GoLab server is written in compiled Go, it easily avoids the dependency conflicts notorious in Python virtual environments. The deployment mechanism relies entirely on Go's native module network, triggered by a single terminal command. That command silently pulls the latest server release directly from GitHub and executes it in memory. There is no traditional installation process. This network gateway diagram illustrates the next step. The local server initializes communication on port 9090. You must supply a Colab token environment variable to secure the local WebSocket. This ensures the port is protected against unauthorized browser access. Once secured, we can track the sequence triggered when the AI agent initiates the Open Notebook tool, routing data directly to the Colab domain. The agent provides a raw Google Drive file URL. The GoLab binary intercepts this string locally. The server mutates the URL, injecting the necessary MCP mapping parameters into the string before passing it to your browser. This injection forces the Colab front-end UI proxy to actively attach to the local WebSocket listener. Your web browser becomes a passive, secure tunnel connecting the local IDE to the remote GPU. This tunneling mechanism entirely bypasses the need for custom API wrappers or complex authentication hacks. Moving past the connection pipeline, this technical schematic lays out the 27 distinct nodes available to the agent, grouped into read, write, and execute clusters. By supplying these capabilities, GoLab elevates the AI from a code generator into an orchestrator of the remote virtual machine. The first cluster contains state-reading tools like Get Environment and Get Notebook Outline. These scan the remote machine to build exact system context for the local agent. The second cluster holds execution tools, notably Run Code Cell and Get Cell Output, which directly trigger physical hardware processing on the remote GPU. The Get Cell Output tool is particularly thorough. It captures standard text, complex tracebacks, and even base64 image data straight from the runtime. This animation illustrates the final cluster, precision editing. Tools like Edit Cell Lines and Insert in Cell target specific middle sections of the code, leaving the surrounding lines untouched. Precision editing addresses a core inefficiency in remote execution. It prevents the AI from needlessly rewriting and transmitting entire notebooks over the network, which significantly reduces redundant bandwidth and token usage. These tool executions are communicated using strict bidirectional JSON payloads defined by the MCP standard. The agent constructs a schema locally, and GoLab seamlessly maps that intent to remote CRUD operations on the Colab cell matrix. This dense tool API completely transforms your static local IDE into a remote control cockpit for the cloud-hosted GPU runtime. This brings us to a central software engineering question. Why build an MCP server in Golang when the target platform, Google Colab, is deeply Python-centric? To answer that, we have to look at the official Python MCP implementation, which relies heavily on dynamic tool rendering. This animation demonstrates the major flaw in dynamic MCP servers. The client IDE node on the left is forced to constantly poll the server for state changes using list-changed notifications. This constant polling creates a fragile dependency. If an ephemeral connection token desyncs, the link breaks, and tools will suddenly disappear from the IDE. The visual resets here to show GoLab's engineering counter-approach, a strictly static tool architecture. GoLab dictates all 27 available tools upfront. It completely eliminates the need for complex client support or dynamic listening protocols. The practical result is guaranteed out-of-the-box compatibility with standard MCP clients, from Cursor to Claude Desktop. Prioritizing static, immutable configurations over dynamic flexibility ensures the connection remains stable, even if the browser violently disconnects and reconnects. But before integrating this into a daily workflow, we need to look at the reality of deploying experimental proxy software in serious production environments. The GoLab codebase is deeply nascent. It is a version 1 release maintained by a single contributor. This diagnostic dashboard highlights the metrics that signal risk to a senior engineering team. The repository has exactly 0 unit tests, low star counts, and merely 6 commits in its total history. Beyond code quality, the system runs into hard platform constraints enforced by Google Colab's strict security sandbox. The largest bottleneck involves Google Drive integration. Google enforces a mandatory interactive OAuth consent pop-up before allowing file system access. Because the GoLab AI agent operates headlessly, it cannot physically click accept on that security pop-up for you. This creates a mandatory manual workaround. You must natively mount the drive in the Colab UI yourself before the AI can execute tools like list drive or read file. You have to weigh these severe limitations against the immediate value of eliminating the copy-paste feedback loop. Despite its flaws, GoLab's static Golang binary provides the most pragmatic, deterministic bridge to remote Colab compute currently available. It solves a critical workflow bottleneck for ML engineers, making it a highly effective, if risky, addition to your local toolkit. Subscribe to the channel for more technical deep dives into the tools shaping modern development.